This problem session is a continuation of the Chapter 8 practice problems at the back of your lecture notes. And we'll start with number 10, which begins questions related to polymers. We will look at polymers and then at unit cells and then at band theory in this problem session. Number 10, draw the addition polymer that can result from the following monomer. Now you need to know what an addition polymer is. So in addition polymers, the molecules simply add together without the loss of any atoms. Addition polymers is that the monomers add together without the loss of any atoms. And in contrast to that, condensation polymers occur when atoms are lost when the monomers add together. Atoms are lost when the monomers add together. We could say when they polymerize. And specifically, we'll look for the loss of water or the loss of HCl. Those are two common molecules that can be lost in a condensation polymer. But this asks, what is the addition polymer that results? Now, we're not going to lose any atoms here. And so in the addition polymer, just keep all the atoms here. We'll have CH2, and instead of a double bond here, we'll take a single bond to a CH and a CH3. Now, as I look at this, by taking away this double bond, this carbon has 4 bonds. It's got doubly bonded to the carbon, that's 1, 2, and it's attached to 2 hydrogens, that's 4 bonds. But now this one only has 3. It's a single bond to carbon, and to 2 hydrogens, it's only got 3 bonds, so it must be attached to something else. This carbon only has 3 bonds, 1 to this carbon, 1 to this carbon, and 1 to this hydrogen, so it must be attached to something else. And so this is the repeating unit. And this repeating unit then is attached to another unit of itself, H2C, CH, CH3. Okay. Now, I put the H2 first. That actually looks a little bit odd. I probably should have written CH2 first like this. CH2, CH, CH3, and this will be attached to the next one. I can put a big parentheses here in, and this just says this is repeated over and over a huge number of times. And within this is the smallest unit. This is the smallest unit right here. It's an addition polymer. When I added these together, I didn't lose any hydrogens. I have the same number of hydrogens here, the same number of carbons in each repeating unit that I had in the monomer. This is the monomer, and this is the polymer. We can draw this polymer using a line structure. All of these are carbon-carbon single bonds. When carbon has 4 single bonds, it is tetrahedral about the carbon with 109.5 degree bond angles. And the line structure sort of gives you that idea. 2, 4, 6, 8, etc. I'm going to put another parentheses around here with N, so that repeats over and over. And every other carbon, there's a CH3 group attached, which I can just put those lines. Every other carbon has CH3 groups attached. So this is what this looks like when we draw a line drawing. Let's look at the next molecule. By the way, this is this monomer, and you don't have to know the names, but this is propylene. Propylene. It's also called propene or propene, but propylene is the old name, and so this is polypropylene, which is a very common polymer that's made industrially, used in many different applications. This next molecule, what is the monomer that prepared this addition polymer? Well, as we look at this particular polymer, and we can see the individual units here, so that this is a repeating unit, this is a repeating unit, this is a repeating unit. So what are the repeating units? This is a repeating unit. So if I were to draw the repeating units would be a CH2. Now, why is it a CH2? Well, this carbon, I see two of the bonds, so there must be two hydrogens, a CH2, and then this single bond to, this would be CH, because there's three bonds here, there must be a hydrogen, attached to a benzene ring. So that six-membered ring with alternating single double bonds is a benzene ring attached to something else. So this is the individual unit in the polymer. But the monomer then, in addition polymers, most of the addition polymers, just like the one up here, start with double bonds that they lose a double bond to form the polymer. So the monomer in this case was CH2 double bond CH attached to a benzene ring. Now again, you don't have to know the names of these particular compounds, but this is the molecule styrene, and so this polymer is called polystyrene. Polystyrene is the type of polymer present in a styrofoam cup. So the key is that each carbon must have 4 bonds. This is the monomer. If this is the polymer, this is the monomer, the single unit, and each carbon has 4 bonds. So when I take it out of the polymer, there's only a single bond here. There has to be a double to give this carbon 4 bonds. It's attached to 2 hydrogens and a double bond to carbon. That gives it 4 bonds. This carbon has 2 bonds to the carbon before. It's bonded to hydrogen and bonded to this benzene ring. So it has 4 bonds as well. Now we're going to look at a series of polymers, and we're going to determine if they are addition or condensation polymers. We'll also determine if they are polyesters or polyamides, and we'll try to identify the monomers that result from forming them. Now, one of the things that will help as we do this is to focus on the individual repeating units. Focus on the individual repeating units. And if you look at this, this is what type of a linkage? This is an ester linkage. And since that's an ester linkage, that means that this is a polyester. This is a polyester. And a polyester is a condensation polymer that was formed from 2 monomers. So here are 2 possibilities. Now, here's part of it came from right here. I'm going to put a squiggle line right here between that C double bond O, because see the C double bond O here, I'm going to put a line right here. So it could be formed from these 2 monomers. So here's a benzene ring attached to a C double bond O, and we could have an OH here, and this is a C double bond O, and we could have an OH here as one of the monomers. Now, how did I get this? I'll show you how I knew it was this in just a minute. Now, let's go to the other side, which is HO, CH2, CH2, OH. Okay, so I knew this was this molecule because in picking this, here's the loss of water. So this involves the loss of water. So in this particular case, this compound is called a dicarboxylic acid. It's a carboxylic acid. So one of the functional groups that I want you to know is that if you have a C double bond OH, that's a carboxylic acid. This molecule has 2 carboxylic acids. This is a dialcohol. There's 2 OHs. This is a dialcohol. Okay. And losing the H and the OH, you can see that it forms this molecule. And then the OH here is also going to be lost along with this H as the molecule continues. Now, since I have 2 different molecules, two different monomers that make this up, then this is also referred to, the polymer is also called a copolymer. A copolymer. A copolymer is a polymer that is made up of two different monomers. So this copolymer has two different monomers. So this involves the loss of water. Involves the loss of water. When the monomers come together, it loses two hydrogens and one oxygen. That makes it a condensation polymer. So higher up on the page, a condensation polymer is when you have atoms are lost when the monomers polymerize. The word that we use, atoms are eliminated or molecules are eliminated. And in this case, a molecule of water is eliminated. There's another set of two monomers that could form this. Instead of a dicarboxylic acid, if we replace the OHs with the chlorine, then we could have the loss of HCl. So another possible way to make this would be involving the loss of HCl. So those are the two that we've shown you several examples of that you should be prepared to see. So that would look like this. Instead of an OH here, there'd be a Cl attached to C double bond O attached to a benzene ring, C double bond O attached to a Cl. Now we still have over here the dialcohol, and this time for the loss of HCl, it'll lose this HCl. This C double bond O becomes directly attached to this oxygen for an ester linkage. So those are two ways that we could form this polyester from either the dicarboxylic acid or this compound. Instead of having an OH group, there's a chlorine in each case. This involves the loss of water. And on the other side as well, this chlorine would be lost, and this H would be lost on this side to continue it on and make this continue. So it's a polyester because this is an ester linkage. And it's a condensation polymer. We have two different monomers. And whenever two different monomers combine to make a polymer, it's called a copolymer. Okay, so let's look at this one. First, focus on the type of linkage that you have. This is an amide or amide. An amide or an amide. And so this is a polyamide. A polyamide. An amide is one that has C double bond O attached to a nitrogen. Now, it came together from two different molecules involving the loss of atoms, and so this is a condensation polymer. It's going to be formed from two different monomers as well, so this is also a copolymer. The two different molecules that could be lost in forming this are water and HCl. So let's do it with water first. So if we look at this much of the molecule right here over here, this could be a dicarboxylic acid. So this could come from a dicarboxylic acid where we have an OH attached to C double bond O attached to a benzene ring. Now that's a carboxylic acid. A carboxylic acid is one that has C double bond O, OH. And this is attached on this end to a C double bond O, OH. So this is once again a dicarboxylic acid. Then this can combine with a diamine. A diamine. So here's a nitrogen. Nitrogen typically has three bonds, so there's two hydrogens. This is attached to a benzene ring, attached to another nitrogen with two hydrogens. And in this case, there's going to be a loss of water. So this involves the loss of water. It's a condensation reaction. And the carbon that was attached to this OH, it becomes directly attached to the nitrogen. So we have the carbon directly attached to the nitrogen. Then this OH on this side will form a bond to a hydrogen from another molecule here. And so this is a diamine. A diamine. There are two amine groups here. And this involves the loss of water. A condensation polymer is formed when two monomers come together and lose a molecule. One of the molecules that's frequently lost is water, the loss of H2O. So that's one way that we could make this polyamide. Another way to make this polyamide is instead of with the loss of water, we could lose HCl. And for HCl, we would, instead of losing an OH over here.
Okay, I found this on the web for HCl and for HCl. Check it out.
I don't know why my phone started talking to me, but in order to, I probably should cut that out of the tape, but I probably won't. So those of you who watched it this far will have something to laugh at, okay? So instead of the loss of water, we're going to have the loss of HCl. So instead of an OH here, there'll be a chlorine atom. So Cl attached to C double bond O, a benzene ring attached to C double bond O, and a Cl. And here's the same diamine. Here's the benzene ring. And this time, there's going to be the loss of HCl. So we'll lose an HCl. The carbon becomes directly attached to nitrogen. And this HCl will be lost to another molecule. And one of the hydrogens here will be lost to the other end. And so once again, this is two different monomers joining together to make this condensation polymer. So it's a copolymer because it comes from two different monomers. This involves the loss of HCl. Okay, and the last example on this page, we've got this as our polymer. Now, it's not a polyamide. There's no functional group. This is all hydrocarbon. It's not a polyester. There's no oxygen functional group like we had up here. Here's a polyester right up here. Here's a polyamide right here. This molecule does not have either of those functional groups. And as I look at each repeat unit, this is a repeat unit, this is a repeat unit, this is a repeat unit. So if I were to draw the smallest repeat unit, the smallest repeat unit looks like this. A C with a CH3 here, a CH3 here, and a CH2 that's attached to something else. That's the smallest repeat unit. Now, this tells me that the monomer must have had a carbon-carbon double bond here. So the monomer is C double bond CH2 with this carbon attached to a CH3 here and a CH3 here. That's the monomer that's present. And when these monomers, there's the same number of atoms here as here, so that means we're not losing any atoms, and so this is not a condensation polymer. So as I look at this, this is an addition polymer. An addition polymer. It's not a copolymer because there's only one monomer that made that. It's not a polyester or a polyamide. It's an addition polymer, and this is the monomer that made it up. Okay, as we go to the next page, now we're going to shift gears out of polymers and talk about unit cells. So as we talk about unit cells here, I'm going to mention one thing that I'm going to provide for you on this exam. On the exam, I will give you these formulas on the front page of the exam underneath the periodic table. These are the edge lengths of 3 of the cubic cells: a simple cubic cell, a body-centered cubic unit cell, and a face-centered cubic unit cell. These are the edge lengths for those, so you don't have to memorize that. That will be provided on the exam. So let's look at what do you need to know about each of these. Well, you need to know, in the first 3 cases, you need to be able to know how many atoms per unit cell are present. So let's do a simple cubic unit cell. Now, if I draw a cube over here, so here's a cube. We're going to draw this back, connect these. So draw this back and connect these. In a simple cubic cell, I have an atom at each corner of a cube. So this represents a simple cubic unit cell. If I want to see this one in back, it's going to go back. I'll draw the dashed lines. This is behind the plane of the paper, and that one's in back. This is a simple cubic unit cell. Now, to determine the number of atoms that are present per unit cell, each one that I see, this is 1/8 of an atom. 1/8 of an atom. Now, that's because if you look at the cubes stacked together, so if I have, this is a cube stacked next to this one, and if I were to put another cube right here, and another cube right here, okay. Now focus on this one. Now you can see this atom is shared by 4 cubes. But I've drawn 4, but there are 4 more cubes on top of it. So each cube has 1/8 of the atom. There's 8 cubes come together at this point. So there's 1/8 of an atom. And so as I look at this, there are 8 corners to a cube. So to get the number of atoms per unit cell, it's 8 times 1/8 is equal to 1 atom per cell. So this is something that you should be able to determine, 1 atom per unit cell. Okay, for a simple cubic cell. For a body-centered cubic cell, now once again I'm going to draw a cube. And there will be an atom at each corner. And let's go ahead and draw this. So there's one right here. But a body-centered cubic cell, there's another atom dead center in the middle of that cube. Okay? And so as I look at this one, how many atoms per unit cell? Well, first of all, we have the one in the middle. So there's 1 plus, and then at each corner there's 1/8 of an atom, plus 8 times 1/8. And so that adds up to 2 atoms per unit cell. 2 atoms per unit cell. Okay. And then let's look at a face-centered cubic cell. In a face-centered cubic cell, I'll draw a cube again. Okay. So I've got an atom at each corner of the cube. Now I'm not going to draw the other ones, but a face-centered cubic cell, there's also an atom right in the center of the face. There's one in the center of this face. There's one in the center of this face. Now, if you focus on this particular one, 2 cells are right next to each other. So here's another cubic cell. And you can see that the one in the center of this face, it's shared by 2. So the one in the middle is half of an atom, whereas the one at each corner is 1/8 of an atom. So to determine the number of atoms per unit cell, there are 8 corners, and each corner has 1/8 of an atom. But there are 6 faces to the cube, and each face has half of an atom because it's shared by 2. So 1 plus 3 is 4 atoms per unit cell. 4 atoms per unit cell. Okay, so I want you to know how many atoms per unit cell. The next thing I would want you to know about these 3, so I want you to know a lot about these 3. I want you to know what the coordination number of each one is. Now, the coordination number is the number of nearest neighbors. The coordination number is the number of nearest neighbors. And if I focus on this atom, then you can see that this atom, it's close to this one in back. It's close to these 4 in the plane. So 1, 2, 3, 4 in the plane, 1 behind, and 1 in front. That's a total of 6. This has 6 nearest neighbors. The coordination number in a simple cubic cell is 6. So again, there's 4 in the plane, there's 1 in back, and there's 1 in front for a coordination number of 6. The coordination number is the number of nearest neighbors. For a body-centered cubic cell, if you focus on, let me draw another cube here so it won't get too busy. Here's another cube, and remember we've got an atom at the corner, at each corner of this cube, and so I've also got one in back here, and I've got one right in the middle. Now that one that's right in the middle of the cube, if we look at how many nearest neighbors it has, well, 1, 2, 3, 4, 5, 6, 7, 8. The coordination number is 8. The one in the middle is next to 4 at each corner, so the coordination number is equal to 8. Coordination number is equal to 8. Now for the next one, how many is it closest to? Well, if I look at this one that's in this, it's on the face. It's a face-centered cubic cell. There's an atom right here. Well, it's close to 4 here. 1, 2, 3, 4. It's close to 1 here and 1 here. That's and then which is 5, 6, and then 1 in back, 1 in front, 7, 8. It's close in all to 12. It has 12 nearest neighbors. The coordination number is equal to 12. Now, that's kind of hard to see here, so I'm going to show you a picture of this. But let me just say this. I do want you to know that the face-centered cubic is the same as cubic close packed. Cubic close packed. Okay. And so I want you to know this, and I will give you, on the front page of the exam, the edge length for a simple cubic, body-centered cubic, and face-centered cubic, FCC, and that a face-centered cubic is the same as a cubic closest packed. Now, it's hard to see how, it's very hard to see how the central...
Okay, I found this on the web. For now, it's hard to see how...
my phone's talking to me again. I'll just move it over here. It is hard to see how this is 12 in the drawing that I had, so I'm going to show you from the book. Here's what I want you to know about hexagonal close packed and a face-centered cubic. When we look in the textbook, and I'm in the textbook on page 246. So for a hexagonal close packed, it's not a cubic structure. Instead, what we see is on the lowest level, the atoms are packed as closely as they can be here. And then the second layer, the atoms go into one of the holes. And then the third layer for hexagonal close packed is that the third layer goes directly above the first layer, so that this is an ABA level. So that notice this one in front, on the third level, it's directly above. It's in this hole. It's an ABA structure. That's hexagonal close packed. Now, if you can see that this is hexagonal close packed, how many closest neighbors does this middle atom have? Well, there are 6 here. 1, 2, 3, 4, 5, 6 in this plane. And it's also touching these 3 atoms. And then 3 more here. So 3, 6, 9, 12. The coordination number here is 12. Now, that's hexagonal close packed. So what do I want you to know about hexagonal close packed? I want you to know that the coordination number is 12. And I want you to know that in the hexagonal close packed, know that the structure for this is a close packed structure with AB, AB, AB. That's the structure. So that as you stack them, it's AB, AB. But the face-centered cubic, which is the same as cubic closest packed, I want you to know that it is ABC, ABC. So how do we get ABC for a cubic close packed, which is the same as a face-centered cubic? Well, in this case, the third layer, the black represents the third layer, it's not directly above the second layer. If it were directly above the second layer, it would be right here. Instead, it's moved over. See, up here, this is directly above the first layer, but here it's not. Here this has been shifted up here, so it's A, B, C. Now it still has a coordination number of 12. Focus on this center atom. There's 6 in the plane, 3 on top and 3 on the bottom, so the coordination number is 12. That's the easiest way to see the coordination number. Now it's hard to see looking at this angle. It's hard to see that this is the same as a face-centered cubic, but you need to know that it is a face-centered cubic, and that the coordination number is 12. Now, the number of atoms per unit cell, I'm just going to put in parentheses that there are, for hexagonal close packed, there are 6 atoms per unit cell. However, that will not be asked on the exam. I will ask these because you can see how many atoms per unit cell. You can reason it out. It's not memorizing, it's reasoning it out. But you will not be asked this. I do want you to know that coordination number is 12 because that implies that you know what I mean by the ABC, ABC, or the AB, AB, AB structure. So that's what I want you to know from the basic cell structures. Now you can use these in calculations, and the next two show you 2 kinds of calculations. There are other calculations at the end of the chapter that illustrate what you need to do in order to solve this. So this says silver forms a face-centered cubic unit cell with an edge length of 409 picometers. What is the radius? Well, this will be given to you on the exam. You'll be given that a face-centered cubic has an edge length equal to 2 on the square root of 2. And so, since you're given that, we know that the edge length for this, the edge length of a cubic cell is equal to 2 on the square root of 2 r. Okay? And therefore, the edge length is given 408 picometers, so 2 on the square root of 2 r is equal to 408 picometers, or r is equal to 408 picometers divided by 2 on the square root of 2. And when you divide that out, you will get 144 picometers. That is the approximate radius of a silver atom. So in this case, you know the edge length, you can get the radius of an atom. That's one way that a question can be asked. Another way that a question could be asked. Iron forms a body-centered cubic. Now you have to use the appropriate formula, obviously. This is face-centered cubic. This is body-centered cubic. And what you need to do here, we're given the radius of an iron atom. Based on that, what is the estimated density of iron? Well, density is equal to mass over volume. And so I can calculate for the mass of 1 unit cell divided by the volume of 1 unit cell. So the mass of 1 unit cell over the volume of 1 unit cell. Okay, so let's calculate the mass of 1 unit cell. Now, what I need to know to get the mass of 1 unit cell is I need to know how many atoms are in 1 unit cell. In a body-centered cubic structure, if you look back up here, here's a body-centered cubic cell. There are 2 atoms per unit cell. So you have to know that there are 2 atoms per unit cell. So I'm going to start with 2 atoms per unit cell. Okay, I'm going to convert this to moles because I want to use the molar mass to get the mass of 1 unit cell. There's Avogadro's number, 6.022 times 10 to the 23rd atoms per 1 mole of atoms. And then I'm going to use the molar mass of iron from the periodic table. The molar mass of iron is 55.85 grams of iron per 1 mole of iron. And so the mass of 1 unit cell whenever we multiply that out, it will be 1.855 times 10 to the negative 22 grams. Now, I only have 3 significant figures at the end of the calculation because this has 3. Everything is multiplying and dividing. I'm going to keep 4, though, on both the numerator and denominator in order to avoid round-off error. So this goes in the numerator. This is 1.855 times 10 to the negative 22 grams. Now I need to know the volume of 1 unit cell. So let's come over here. I'm going to draw a line over here. The volume is equal to the edge length cubed. It's a cube. What's the volume of a cube? If I know the edge length of a cube, I cube that. It's the edge length cubed. Well, what is the edge length of a body-centered cubic cell? You don't have to memorize this. It's on the exam. It's 4r over the square root of 3. So 4 times r, 124 picometers, over the square root of 3. And that entire quantity is cubed. Now, whenever we do that, this is going to be in cubic picometers. And generally, density is in grams per cubic centimeters. Let's go ahead and multiply this out. So it's going to be 4 times 124 divided by the square root of 3. And then all that entire quantity cubed, which is in picometers, 2.348 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 10 to the power of 7 cubic picometers. Now I want to convert this to cubic meters. So the number, the volume in cubic meters, I have 2.348 times 10 to the power of 7 cubic picometers. Now I'm going to go from picometers to meters. Pico means times 10 to the negative 12. The 10 to the negative 12 goes with the base unit, 10 to the negative 12. And I have to cube this entire quantity. Now I'm going to go from meters to centimeters. Centi means times 10 to the negative 2. This goes with the base unit, and I have to cube this whole quantity. So this will give me the answer in cubic centimeters. And I get 2.348 times 10 to the negative 23 cubic centimeters. Okay, so that's the volume. It's a cube. I know the edge length, and so the volume of a cube is you cube that value. So I divide that up here, 2.348 times 10 to the negative 23 cubic centimeters. And this will give me units of grams per cubic centimeters. And so when we calculate this out, we get 7.90 grams per cubic centimeter. That's the estimated density of iron based on that radius, given that it's a body-centered cubic. Okay, the next thing that we want to look at here, the last topic has to do with semiconductors and band theory. So what type of semiconductor, N-type or P-type, would result from the following? Now, if I'm looking at this, germanium is this semiconductor, and we're doping it with boron. This is the dopant. Now, germanium, as I look at germanium on the periodic table, here's germanium, and we're going to dope it with boron. Germanium has 4 valence electrons, 4s2, 4p2. Boron has 3 valence electrons. It has fewer valence electrons. So boron has fewer valence electrons than the dopant. And that means that if there's fewer electrons, it's got holes, and that means, therefore, that this is a p-type semiconductor. This is a p-type semiconductor. If the dopant has fewer valence electrons than the semiconductor, then the electricity will be conducted through the positive holes, so it's a p-type semiconductor. Okay. And if you have silicon doped with phosphorus, then silicon is my semiconductor. This is the dopant, and so we have to ask, does the dopant have fewer electrons or more electrons, valence electrons, than the semiconductor? Here's silicon and here's phosphorus. Phosphorus has more valence electrons than silicon. This has more valence electrons than silicon. Since it has more valence electrons, therefore, this is an N-type. It conducts electricity through the negatively charged electrons, and it's an N-type or negative semiconductor. And the final question, which of the following has the smallest band gap and which has the largest band gap? Well, the simplest way to look at this is that copper is a conductor, silicon is a semiconductor, carbon is an insulator. And so based on that, the conductor has the smallest band gap. Actually, it has no band gap. And the insulator has the largest band gap. So what does that mean? Well, if we look at copper, if I draw an energy diagram, and this is copper, then copper, here's the conduction band, here's the valence band. They're butted up right next to each other, and there's no band gap. That's what we see with metals, which are conductors. If I were to look at silicon, so here's silicon, then there's a small band gap in a semiconductor. So this is the valence band, this is the conduction band, and there is a small band gap. And if we were to look at the last one, where we have carbon. Carbon is an insulator, so this is my energy diagram. Here's the valence band, here's the conduction band, and there's a large band gap. So in each case, I've drawn up here, this is the conduction band. When electrons get into it, they can conduct electricity. This is the valence band. This is where all the valence electrons are. When there's no band gap, then it takes virtually no energy for the electrons to hop up here. At room temperature, there's enough energy that the electrons can hop into the conduction band and conduct electric current. In a semiconductor, there's a small band gap, so it takes a little bit of energy. And the higher the temperature, the more energy, so that the higher the current that can be conducted. But in an insulator, such as carbon, where there's a large band gap, even at high temperature, there's not enough energy to get the electrons from this lower energy valence band to the higher energy conduction band.